The theory of time before the Big Bang is one of the most fascinating and mysterious in the universe. According to the standard model of the Big Bang theory, space and time arose simultaneously as a result of the Big Bang, about 13.8 billion years ago. It indicates that the question of what came before this event is completely wrong, since we know that it was not before the Big Bang. In fact, the Big Bang marks the beginning of time. Some physicists believe that space still exists and does not conform to traditional methods of measuring time. In this scenario, events as we know them could not have occurred because the very basis of time progression was missing. Discussions around this period often lead to the exploration of alternative timelines or conditions of existence where the rules governing our universe might not apply. Other theories consider the possibility of a cyclic universe in which it expands and contracts endlessly. According to this model, the Big Bang is not a definitive beginning, but rather a transitional point in a continuous cycle of creation and destruction. This view opens the door to meaningful discussions about events that may have preceded our current universe, although these ideas remain speculative and difficult to test. These studies push the boundaries of our understanding, inviting us to reflect on the limits of scientific inquiry. The search for the meaning of time before the Big Bang emphasizes humanity's deep desire to comprehend not only the origin of the universe, but also the fundamental nature of reality itself. This raises profound philosophical questions about the existence, flow of time, and what before might even mean in a context where time as such does not exist. As we approach the Big Bang singularity, our conventional understanding of time begins to break down in surprising and complex ways. In this singularity, the equations of physics, especially those set forth in the general theory of relativity, reach a point where the curvature of space-time becomes infinitely steep. This presents a situation where the laws governing the creation of the universe are not working as we expect, and our traditional theory of time becomes irrelevant. At the time of the Big Bang, the density and temperature of the universe were very high, so extreme conditions arose. In this environment, time as we know it, a linear sequence of past, present, and future, is no longer a true measure. It appears that all events will converge to the point where our time falls away. Thus, trying to use the standard rules of time leads us into a world of paradoxes and confusion, where words like before and after are not understood. This disintegration of time shows the limitations of our current scientific knowledge. Although quantum mechanics can understand the behavior of particles on very small scales, it is not yet adapted to the larger scales of general relativity. Approaches such as quantum mechanics aim to fill this gap, offering a possible way to understand the nature of space-time in unity. However, these concepts are still present in theoretical physics and raise some questions. The consequences of this collapse challenge our understanding of reality and force us to rethink the way we live. They encourage thinkers and scientists to go beyond traditional limits, exploring not only what it was like before the Big Bang, but also what it really means to experience time and space in a universe marked by such an extraordinary beginning. The quest to understand the role of time in space ultimately enriches our appreciation of the complex nature of reality itself, drawing us into the depths of mysteries that lie beyond our current knowledge. Imaginary time is a compelling concept introduced by theoretical physicist Stephen Hawking to help make sense of certain cosmological phenomena, especially in relation to the early universe. Simply put, imaginary time is a mathematical construct that arises when time is treated as a complex rather than a real number. In this context, while we normally think of time as flowing from past to future, imaginary time allows us to envision time as a dimension that behaves more like space, where the standard distinctions between past and future can become blurred. In Hawking's model of the early universe, the use of imaginary time helps solve the singularity problem associated with the Big Bang. The transition from real time to imaginary time effectively smooths out the infinite densities and temperatures that arise in a singularity. Using this approach, the notion of an initial boundary or starting point of the universe can be conceptualized as a rounded surface rather than a sharp edge. It leads to the idea of a self-contained universe with no beginning and no end, and eliminates the need for a traditional starting point. Imaginary time plays an important role in cosmological models that describe the evolution of the universe according to quantum mechanics. According to Hawking, when imaginary time is applied, it becomes easier to visualize the early universe as a kind of four-dimensional sphere known as a state of no boundaries. This concept allows scientists to explore scenarios in which the universe does not have a single point of creation, but rather is a seamless fabric of space and time that expanded from a state of high energy and density. Exploring the concept of imaginary time forces us to rethink our assumptions about the very nature of the universe and its origin. This challenges the traditional linear perspective of time, prompting us to consider a more complex and nuanced understanding of how the universe may have come into being. In this case, we can talk about initial conditions and the very fabric of reality itself. These theoretical explorations serve not only to illuminate the mysteries of the cosmos, but also to better understand the fundamental role of time in shaping the universe we observe today. Various pre-Big Bang theories address the concept of time in different and intriguing ways, each offering a unique perspective on what may have existed before the beginning of our observable universe. One well-known model is the cyclic universe theory, which assumes that the universe goes through endless cycles of expansion and contraction. In this concept, time is not linear, but rather works in cycles, with each cycle leading to a new Big Bang, followed by a period of expansion. This approach implies that time does not have a finite origin, but rather is a continuous process shaped by the repetitive nature of the universe. Another theory that considers the concept of time is the equipartition scenario, which suggests that our universe arose from the collision of two three-dimensional branes in a higher dimensional space. According to this model, time may have existed in some form before the Big Bang, having arisen as physical conditions changed radically as a result of the interaction of these branes. In this case, time behaves as a dynamical variable that can change depending on the interaction of the fundamental structures of the universe, offering a perspective in which time has a different history and shape than in our usual understanding. Quantum theories of gravity also provide compelling insights into the time before the Big Bang. These theories explore how time and space might behave under conditions where quantum effects cannot be ignored, typically at very high energies. In this case, time may lose its usual structure and behave not as a linear progression, but as an emergent phenomenon arising from more fundamental aspects of the universe. Some proposals within these theories suggest that, at the Planck scale, the very concept of time may dissolve into a network of interconnected quantum events, where temporal distinctions become meaningless. Finally, the concept of timelessness arises in speculative discussions of the state before the Big Bang. Some physicists argue that if the universe emerged from a quantum state, traditional time may not have existed. The early universe can be described by a timeless realm where space and events existed in a superposition of possibilities, suggesting complex relationships between time and existence that challenge our basic intuitive notions. Each of these theories demonstrates diverse and rich approaches to understanding time in the conditions preceding the Big Bang, pushing the boundaries of our knowledge and inviting further exploration of the true fabric of reality. The arrow of time is a term for the single direction in which time flows. Many times it shows different aspects of this situation. The most famous thermodynamic arrow comes from the second law of thermodynamics. This law states that in an isolated system, entropy or disorder increases with time. As a result, we see how physical processes flow from low entropy states to higher entropy states that show a direction in time. Another important arrow of time is the mental arrow, which represents the human perception of time. It indicates that we should remember the past rather than the future, as our memory is tied to the flow of experience. There is also an arrow corresponding to the expansion of the world, showing that time moves forward in accordance with the growth and development of the world's infrastructure. The situation becomes really complex and interesting if we consider the behavior of the arrow of time before the Big Bang. If we accept the time we know began with the Big Bang, the question arises, what does it mean to speak of a time prior to this event? Some theories suggest that before the Big Bang, the arrow of time may not have existed in the usual sense. Conditions in the pre-Big Bang scenario could have been so fundamentally different that our current notions of time progression and causality would be inapplicable. In some speculative models, such as the cyclic universe theory, the arrow of time can change with each cycle, resulting in a different orientation of time in each iteration. This presents a fascinating context in which time can behave in ways that are not only unusual to our everyday experience, but also calls into question the very nature of time itself. If time in some form existed before the Big Bang, it may have been characterized by a state of low entropy that transitioned into the higher entropy state we observe today, thus giving rise to the directionality of the arrow of time. Ultimately, the concept of the arrow of time raises profound questions about reality and existence. As we explore the mysteries of the origin of the universe, understanding how time functioned in those early moments, or even earlier, helps us further understand the mechanisms that govern both the cosmos and our place in it. By exploring these complex relationships, we gain a deeper understanding of the fundamental nature of time itself. Entropy plays a critical role in our understanding of time and its directionality, especially in the context of the origin of the universe. As mentioned earlier, the second law of thermodynamics states that in an isolated system, entropy tends to increase over time. This principle suggests a natural progression from order to disorder, meaning that systems evolve toward states of higher entropy. Accordingly, our perception of time is closely related to the rise of entropy, as we associate the passage of time with the movement from organized states with lower entropy to more chaotic and disordered states. When we try to apply these ideas to the concept of time before the origin of the universe, it leads to some intriguing questions. If we consider the Big Bang as the beginning of the universe, it is generally agreed that it represents a state of extremely low entropy. This means that the universe must have existed in an even less entropic state before the Big Bang, which contradicts our typical understanding of cosmic evolution. Speculation about a pre-Big Bang state often involves discussion of a high-energy vacuum state, or similar scenario in which entropy is minimized. The idea that entropy could have been even lower than it was at the time of the Big Bang provides a framework for studying what happens to the arrow of time. If time began with the Big Bang, then the increase in entropy would mark our progression forward in time, emphasizing the transition from a highly ordered state to more disordered configurations of matter and energy. This raises the question of whether time as such existed in the universe before the Big Bang. If entropy was at such a low level, then perhaps the conventional arrow of time, which relies on the progression of disorder, did not have the same significance. In addition, studying entropy in the context of pre-Big Bang theories informs discussions of cyclic models or multiverse theories. In cyclic models, each cycle of the universe could somehow zero out entropy, creating a framework in which the concept of time and entropy is constantly being rethought. Through this research, we are trying to understand the complex relationship between entropy, time, and the origin of the universe, shedding light on the entangled nature of reality itself. Understanding how entropy relates to these primordial conditions leads to deep insights into the nature of existence and the underlying structures that shape the cosmos. Quantum mechanics offers intriguing insights that can expand our understanding of the nature of time at the time of the Big Bang, address gaps in our knowledge, and emphasize the complexity of the origin of the universe. At its core, quantum mechanics shows that on extremely small scales, particles and phenomena behave in ways that defy our classical concepts. This framework encourages scientists to rethink how time might have operated in the incredibly dense and energetic conditions surrounding the Big Bang. One important area where quantum mechanics intersects with cosmology is the concept of quantum fluctuations. These fluctuations may have played a key role in the early universe, where the vast high-energy state was characterized by uncertainty and probabilistic events. In this context, time could not follow a linear trajectory as we understand it, but could manifest itself in a more fluid manner where different quantum possibilities coexist. This notion challenges the traditional linear description of time, suggesting that time itself may be emergent, shaped by quantum interactions rather than bound to a rectilinear progression. Further research within quantum gravity aims to unify the principles of general relativity and quantum mechanics. Theories such as string theory suggest that on the Planck scale, space and time may become quantized, that is, have a granular structure, rather than being continuous. If true, this could have profound implications for our understanding of the initial moments of the universe and the nature of time itself at the time of the Big Bang. The idea of a quantum realm permeating the very fabric of space-time might suggest that time in its usual sense loses meaning in the vicinity of the singularity. Furthermore, considering time in the context of entanglement and non-locality, key aspects of quantum mechanics opens new avenues for studying the early universe. Since entangled particles can exhibit correlation independent of distance, the question arises as to how events in the primordial cosmos might have been related. This suggests a more complex and interconnected nature of time progression that may be radically different from our everyday experience. Quantum mechanics invites us to reconsider the nature of time at the time of the Big Bang, potentially revising our understanding of its flow and characteristics. By incorporating quantum principles into cosmological models, scientists can attempt to unravel the mysteries surrounding the origin of the universe and push the boundaries of our knowledge of time and existence itself. Through this research, we can gain a deeper understanding of the fundamental mechanisms that shape reality and the complex relationship between time and the cosmos. The problem of time in quantum gravity touches on a deep and complex issue arising from the interaction between general relativity theory and quantum mechanics. When physicists attempt to create a unified theory that can describe both the large-scale structure of the universe and the behavior of particles at the quantum level, they face serious problems with how time behaves in these different structures. The general theory of relativity views time as a space-like dimension woven into the fabric of space-time, whereas quantum mechanics operates with principles that do not incorporate time in the same simple way. One key aspect of the time problem is that in quantum mechanics, the fundamental equations describing quantum systems do not include time as a variable in the same sense as in classical physics. Instead, the evolution of quantum states is often described by a wave function that captures the probabilities of different outcomes, but does not require a classical view of the flow of time. It poses problems when trying to unify these approaches, especially in understanding how time operates at the earliest moments of the universe's existence, such as those associated with the Big Bang. This problem becomes particularly acute when considering the early universe, where conditions were governed by extreme gravitational effects, making a unified description of space-time and particles necessary. This raises the question, how can we conceptualize time near a singularity? Since traditional models assume that time and space originated at the moment of the Big Bang, the question of what happens to time before or within such a singularity, or how time progression is consistent with quantum states, remains a subject of intense debate. Various approaches have been proposed to solve the problem of time in quantum gravity. One idea suggests that rather than viewing time as a separate dimension, it may arise from more fundamental elements of reality, potentially intertwined with quantum entanglement and relationships between particles. Thus, time can be viewed as an effective parameter due to the dynamics of quantum states, rather than as an independent background against which events unfold. This study of the time problem not only develops theoretical foundations, but also prompts deeper reflection on the nature of reality itself. By grappling with these questions, scientists hope to gain insight not only into the workings of the early universe, but also into the fundamental structures underlying space-time. Understanding how time is related to quantum mechanics ultimately has the potential to change our view of the cosmos and our very existence in it, shedding light on the entangled tapestry of reality. The concept of causality, which describes the relationship between causes and their effects, faces serious problems when considered in the context of conditions prior to the Big Bang. Traditionally, we understand causality as a fundamental aspect of time, where events delineate a clear causal chain. However, the Big Bang marks the point at which traditional conceptions of time and space begin, leading to intriguing questions about how causal relationships might have operated and whether they even existed before that point. In some pre-Big Bang theories, such as the cyclic model of the universe goes through endless cycles of expansion and contraction. Within this framework, causality can be conceptualized as a continuous process where each cycle can influence subsequent ones. While such a scheme provides some continuity, it still raises questions about what before means in a context where time itself is cyclical. If each universe follows the previous one, the relationship between cause and effect may undergo changes with each cycle, complicating our usual understanding. Some models of quantum gravity suggest that in the very early universe, and perhaps even before, the traditional notion of causality may not apply at all. On extremely small scales, especially near the so-called Planck scale, the interaction of quantum mechanics and gravity leads to a reality that is quite different from our everyday experience. In a realm dominated by quantum fluctuations, events can occur without clear cause and effect relationships, as particles can be entangled or exist in a superposition of states. This opens up intriguing possibilities for the interconnectedness of events, where influences may go beyond classical cause and effect relationships. Moreover, if we consider the concept of a timeless state proposed by some theoretical physicists, we find an even more profound departure from established causality. In such scenarios, where neither time nor space is defined in the usual sense, the very idea of cause and effect may disappear. Instead of a linear sequence of events, there may be a set of potentialities governed by the principles of quantum mechanics, where outcomes are determined by probabilities rather than direct causality. The notion of causality before the Big Bang challenges our traditional understanding of how events are related in time and space. This encourages scientists and philosophers to explore complex models that either redefine or subvert traditional causal relationships. By exploring these profound questions, we deepen our understanding of the origin of the universe and the fundamental nature of reality itself, leading to a deeper appreciation of the tangled web of interconnections that can shape the cosmos. The second law of thermodynamics is fundamental to our understanding of the universe and plays an important role in the debate about time before the Big Bang. This law states that in an isolated system, total entropy, or a measure of disorder, tends to increase over time. This principle is important for determining the directionality of time because it emphasizes the natural transition from ordered states to disordered states. When considering the conditions of the universe's origin, the second law helps to frame discussions about what might have happened before the Big Bang, and what implications this might have for our understanding of time itself. In the context of the Big Bang, it is generally accepted that the universe originated in a state of extremely low entropy. The low entropy state means that the universe, as it expanded and evolved, moved toward higher entropy, a critical aspect of its developmental trajectory. Understanding the implications of this transition emphasizes that time, as we perceive it, is closely related to this increase in entropy. In investigating conditions prior to the Big Bang, we are confronted with crucial questions related to the state and behavior of entropy prior to the emergence of the universe as we know it. If we consider scenarios prior to the Big Bang, one possible interpretation is that the universe existed in a state of even lower entropy prior to the Big Bang. This raises an intriguing question. How can we envision a state of existence in which entropy is minimal or zero? Discussions around this idea often lead to assumptions about high-energy vacuum states or fluctuations in the quantum field that existed before the singularity. These pre-Big Bang models suggest that although entropy rose rapidly after the Big Bang, the conditions that inspired the creation of our universe may have been radically different, requiring a re-evaluation of how we understand time in this context. The second law of thermodynamics also allows us to understand more complex models, such as those describing cyclic or oscillating universes. In these models, the universe experiences repeated expansions and contractions, which suggests the cyclic nature of entropy. In this case, each cycle could reset entropy to a lower level, allowing us to view time as a loop rather than a straight line. Such views help expand our understanding of time before the Big Bang, indicating that the relationship between entropy and time may be more subtle than our traditional linear interpretation. Ultimately, the second law of thermodynamics serves as a crucial cornerstone when considering time and the conditions that existed before the Big Bang. It emphasizes the importance of entropy in shaping the direction of time and encourages us to explore deeper questions about the nature of existence, reality, and the processes that govern it. Through this study, we will gain a deeper understanding of how the universe evolved from its original state and how it can update our understanding of time,